So welcome back to our final talk for these 2 days. And we're really excited again to hear from Alison Hill, who will talk about household transmission dynamics in COVID-19 and other infectious diseases. So I'll give you the floor.
Thanks so much. And thanks all of you who have been the consistent attendees on all of these seminars over the past few days. It's been a lot of fun and appreciate your excitement about the science here.
Oh no, this is not working.
It's okay. We tried so hard. Have a clear this time, but no dice. Okay. Great. So just super big picture introduction again for anyone who didn't hear it. Before, my group works on developing mathematical models and computational and statistical tools to help us better understand the dynamics and evolution of infectious diseases at multiple scales. So both within individual patients or hosts and across populations. And we do this by building models that are really inspired by in-depth understanding of the biology and epidemiology behind diseases, finding ways to integrate data from a lot of different sources into our models, and then using models for different purposes, anywhere from comparing our ideas about biological hypotheses driving infection dynamics to observations to making more specific forecasts or projections about either clinical outcomes or epidemiological time courses under different intervention scenarios. So today, I'm going to be talking about a series of projects. They were all inspired by COVID, but actually most of this work is applicable to a broad range of infections, with really the common linking theme of understanding how human transmission networks, and in particular, the role of household transmission on infection. So when you think about infectious disease transmission and your own personal risk for infection, I think these might be the type of settings that people are more commonly think about as high risk, be it like crowded public places, healthcare settings, and other indoor environments. But maybe what we don't think about as much are these other types of contexts that we don't really have the option of changing. So our more intimate interactions with members of our own families and households. But for many, many infections, it has been known for many years that this is really one of the predominant settings of transmission, and something we need to think about more carefully in many contexts to understand how we can best control infectious diseases. So today, just a summary of the topics that I'm going to be talking about. So first, I'll talk a little bit about the influence of household structure and disease dynamics within household on kind of overall ability to control epidemics. Then I'll talk about a project at the intersection of housing policy, disease control, and health equity. And then I'm going to talk about how we can actually use households as a setting for estimating key transmission parameters that are really difficult to estimate in other contexts. So this project, first part, originally got inspired very early on in the COVID epidemic, where we're at the stage where some localities were experiencing really rapid transmission, and as a result implemented very strong measures, social distancing measures to control transmission. And at that time, one of the big questions was really like, how quickly do we expect to see a drop in the burden of COVID-19 in populations after these interventions? And when we don't see that right away, does it mean these interventions aren't working? So here I've just shown some examples of different contexts, different sort of cities or other regions around the world where really strong interventions were implemented very early, like around March 2020. And you can see this common pattern. So these dotted lines are the time of interventions. Before that, you see this rapid exponential growth. And these different curves are different kind of measures of disease burden, anywhere from new cases, blue curve, to kind of more severe disease outcomes. The green and yellow are people in hospital or requiring intensive care, then down through measures of deaths from disease. And you see this common pattern that after lockdowns or stay-at-home orders, similar type measures, there's quite a long time period before you see this turnaround, either in new cases or in hospitalizations, peaking sometimes much later, or in deaths that are being reported. So these long delays. So we are interested in understanding what is the driver of these delays and what role do kind of two factors that we hypothesize would be important here. One, just the natural clinical progression of the disease in patients, but two, the structure of the human contact networks over which disease spreads. So to get at this, we put together a model that took into account both of these proposed effects, and that was really driven by our understanding and our uncertainty about COVID transmission dynamics at the time. So first part of the model is really a relatively standard model for disease transmission and progression. This is the model we used at the time. Of course, if we were doing this today, there's other things we would probably add more nuance, but it doesn't really change any of the main results today. So the basic idea is that individuals are susceptible to disease, can become infected, progress through a latent period to eventually an infectious and possibly symptomatic stage. From there, individuals, some of them may progress to more severe stages of disease requiring hospitalization or more intensive care. From any of these stages, individuals might eventually recover, survive, develop some degree of immunity, or might proceed to death. And in this model, some things that we wanted to be very careful about is using what we best knew at the time about the distribution of time individuals spent in each of those states, and really parameterizing the details of that distribution based on real data, and sort of instead of assuming sort of standard, more easy to model approaches where there's just some kind of continuous rate of leaving those states. That's kind of one part of the model. And then the other part is really trying to construct a realistic, but not too complicated version of human contact networks that took into account the role that households play here. And why we were particularly interested in this role of households and networks is because if you think about what is stay-at-home order or most social distance policies doing, it's reducing contacts you have with individuals outside your household, workplace, school, public transit, community in general, but it's not doing anything to reduce your household contacts. In fact, it might be increasing them as you're spending more time at home. So basically, the idea of the network is something like this, where individuals live in households with a distribution of other individuals and have contacts with everyone in their household, and then contacts with individuals in other households. And we used a lot of different data sources that I won't go through all the detail of now to parameterize this. You can get information from census on distributions of household sizes and composition. And then there are many different data sources that inform the number of contacts of the type that are relevant to COVID spread that people have on a daily basis with individuals outside their households, either broken down by different settings or kind of aggregated. So from that, we were able to come up with a distribution of contacts that individuals have both in their households and outside their households, and construct networks to recreate those statistics. But then there's another aspect here that whenever you make a transmission network, you have to both decide what edges they're going to be, so sort of who is connected to whom, but you also have to think about what the weight of those edges is. And in the case of a transmission model, what that means is that if we say two individuals are connected and there's the potential for transmission between them, is the sort of probability per time of transmission higher along certain contact types versus another. And why this is important in this context, if you think about the type of interactions you have with people that you might share a household with, those might be more intimate, more physically close in some way compared to contacts you might have with a typical member of the community that you would be interacting with. And of course, this is important for disease transmission, particularly for respiratory and sort of contact-based infections like COVID. And this is something that is a lot harder to get at in a data-driven way, especially early on in epidemic. So this we considered a range of values for. So what I'm showing here is a range of values that we considered for the relative weight of these like external contacts compared to household contacts. And in this case, we just assumed they had equal weight. And what these bars are showing is if we assume this particular weight, then how much of the overall transmission potential of disease, which we're summarizing here as the overall basic reproduction number. So on average, how many secondary infections does each person cause? How much of it is composed of spread outside the household versus inside? And for values where we assume that external contacts have a lower weight, so they're have less propensity to transmit, then more of the R naught is composed of household transmission. In cases where we assume external contacts have a higher weight, which isn't a crazy assumption. For example, you might spend a lot more hours per day with your coworker than you do with your roommate. So in that case, sort of assume they have a higher weight, then R naught is more composed of the external contacts. And what this red line here is showing is kind of as a result of these different assumptions, what's the value of one type of metric that we use to quantify household transmission a lot for infections, and something that people do try to measure in studies and eventually did get measured for COVID, which I'll talk about a bit. So it's called the household secondary attack rate. What this means is that if one individual in a household is infected, what's the probability that they will transmit to any other given individual in their household? And depending on these assumptions, so that could be anywhere from around 25% chance of transmission to any given household contact, or up to like 70% or down to 10%. And actually at this time, and kind of still today, there are a range of estimates from different settings for this household infection potential for COVID, like in this entire range.
Is it possible to increase the size of the window?
Yeah, it looks really small and it's making it hard to see. Yeah, why is it not covering the whole screen?
It's coming from your computer.
Yeah, it's okay. I'm just gonna actually, we'll just share the screen normally, see if we'll make it better, because I don't actually need, if we can make it, oh, here, let me get rid of this mode of sharing. I don't know. Yeah, sorry, everyone online, but it is looking really weird in the room.
The rectangle of
Yeah, I know. I'm gonna make it, I tell it not to be, it's so small. Sorry, I look crazy. Okay, now we are going to do this. Let's see if we can improve it. Whoa. Nope. Okay, let me just end this. Why is it going? I didn't even tell it to go in presenter view this time.
Oh, it might be because it's a second screen.
I saw the technician using the mouse to go on.
No, it's not.
Can you just try to put it now in just like regular present,
Yeah.
like just PowerPoint present? Yeah, over to the right, like to. Oh. Try that. So,
On top.
This is not Mike. I don't think
Yeah, like this. Yeah, that's good.
Okay.
well, no, but now you're
Now-
seeing this whole weird thing.
Now if you press full screen. But swap displays.
But it's showing the same thing on both displays. Let me try. Oh,
That's a
yeah,
good
we can
idea.
just do it like this. Yeah, it's not actually important for me
Or
for
you-
this
yeah,
talk
that's
to
good.
see
Okay.
the slides. It's like pretty simple. Yeah, okay, that's better because even I, like, what does it say? Okay, awesome. So right, there's a lot of uncertainty here in the quantitative contribution of household transmission. So we considered a range of values here that we thought kind of encompass the uncertainty in how much transmission occurs in households for COVID. So then using this model, we basically tried to simulate what was happening in this early stage. So infections introduced in a population, it's spreading exponentially, and then at some level that we kind of calibrated to various data sources where some percent of the population, still pretty low, is infected, strong social distancing measures, but not perfect measures enacted. And yeah, like I said, what social distancing measures they're doing is basically removing or downweighting some of these external contacts while not making a difference to household contacts. So what do we see here? So one thing that comes out of these models quite easily is that the long clinical progression of COVID, so from the stage of getting infected to developing symptoms, eventually being reported as a case, to progressing to hospitalization, severe infection, or death, that plays a role in these delays that are seen. So this graph is just showing sort of different stages of the model in these time courses. And basically, what you can see here is that there's a delay between when a strong intervention is implemented and when you might see a peak, for example, in individuals dying or individuals going into the hospital or requiring intensive care. So there's some delay there. And that delay we can quantify here. And part of this delay you get even if you have a completely well-mixed model. So it's really driven by the clinical side of things. But then when you include this more realistic network model, that delay changes significantly. So what this graph is showing is these delays in some different metrics, for example, new diagnoses or new deaths. And when you're including a model that takes into account households versus external contacts, you can get much longer predicted delays until you actually see the peak in some of these outputs. So potentially weeks after the intervention, even if it's quite highly effective. And like I said, we don't know exactly what the contribution of this household transmission is, and that's quite important. So the amount of delay you expect to see here really depends on how transmission potential is spread between household versus external contacts, and kind of in like a nonlinear and unexpected way. So for example, you can see from these graphs that it's actually kind of at intermediate importances of household transmission that you see the longer delays. And then this is showing this in a little simpler way. So here, as a function of how important outside contacts are relative to household, we look at, given the strong intervention, what's like the final percent of the population that's infected, assuming the intervention is staying on indefinitely, which obviously we know isn't true. And what you can see is for whether that intervention is like perfect or imperfect, it's actually at intermediate importances of household transmission that you see the biggest burden of disease despite these interventions. So this is a little bit maybe unintuitive at first, but there is a reasoning behind it. And like basically the way I like to think about it is that if household contacts are, or let's say in this context, so if your external contacts are really important and are the main driver of transmission, then eliminating them by social distancing measures is very effective at reducing spread. Even though you could still spread your household, if that rate is quite small overall, then that doesn't lead to very many new infections. Most infections will like fizzle out within households. At the other end of the spectrum, if household transmission is very important, but external contacts don't play that big of a role, then when you reduce them with a social distancing measure, it doesn't do much to change transmission, and you get very effective spread within households, even if households are somewhat isolated. In this intermediate regime, it's kind of the worst case scenario where when you have these measures, they're not strong enough to completely eliminate transmission between households, but you still have efficient transmission within households. So even with these measures, you can still get some multiplication of disease within households and some sort of leaky residual transmission between households. And this is also related to sort of how many unique households are like seeded with infection at the time that these interventions would be implemented. So I think what this is getting at is like understanding household transmission is actually quite important for predicting how efficacious a particular degree of reduction in general contacts in the population would be. So measuring these type of quantities really early on is important. And if you're kind of interested in going from measures like, oh, I reduce mobility by this much, how will that actually impact when I'm going to see a peak and turnaround of cases, and just how many cases do I reduce overall? You do need to have some understanding for this role of household transmission and including it in a model, which is non-trivial because, you know, still for many models that many people are doing, because of the computational complexity of them, we don't always simulate things on networks, which works for many things, but certain things we don't get right that way. So network structure and the role of households has some more complicated roles too. So here I'm showing a bit of a breakdown of the way that different contributors to overall networks and populations look. So for example, sort of different shapes of networks make up our external contacts, depending on whether they're sort of random community interactions or like school or work or social group interactions. They have really unique shapes suggested by sort of studies that try to measure these things. And one thing that we see is that we know that when we implement these type of measures, it's unlikely that they are kind of just randomly removing connections in a population or evenly downweighting all connections. It's actually more likely that you see this sort of clustering in contact removal, meaning like if certain jobs are not going to happen like in person during an intervention, then many people who all contact each other are now going to have zero contacts, whereas another workplace sector that might be open might not be changed at all. So instead of going from moving this network to something like this, you might move it to something like this, where in one sort of region of the network contacts are eliminated and others they're not. And this actually also has some interesting implications for the long-term outcomes of social distancing-based disease control, in that you can get much longer-term disease persistence in these more realistic scenarios where you're kind of removing clusters of a network and not others. And this is actually like not just general to social distancing-based interventions. Other interventions have a similar property. For example, vaccinating certain communities and not others, where you have whole communities that might not receive that intervention but are still mixing preferentially with each other, can also facilitate disease persistence. And then finally, at this time, we use the model to better understand how different properties of household composition might impact disease risk. So for example, as a function of the size of household, what percent of individuals do we expect to eventually become infected? And you can see here this like stronger than linear relationship between household size and infection risk. This is because generally when you live in bigger households, you both have more chance of infection getting introduced from the outside and like spreading within. Similar, we kind of make some estimates for how the role of having essential workers who are still having outside contacts or not might influence household risk. So these are just sort of theoretical predictions, but many aspects of this kind of qualitatively turned out to be true during COVID. So one of like the drivers of why certain populations have higher disease risk is because they live in larger households, often with multi-generational families and more household crowding. So factors like that can influence disease risk. And similarly, if such households also are more likely to have people working outside the home, this can impact risk. There are certain things that we know now, more complicated aspects of household transmission that mean we can't take these values at face value. For example, when you have larger households, your rate of interacting with each person in the household is actually probably less than in a smaller household. And those are things we can try to estimate now from data. So one final thing we were interested in looking at with this model, because this is something that a lot of different countries and regions were discussing as a potential policy for COVID at the time, was this idea of household bubbles. So we're not ready to completely relax like population level wide social distancing measures. Maybe we can say that people can choose like a few other households that they choose to mix exclusively with, but still not like with the general population. So we wanted to use this sort of model to try to understand how that might impact transmission. So basically the idea is that you have like fusion of households, and now multiple households interact as if they were roughly one household. And model predictions suggest in general that this is like not often a great way of maintaining disease suppression. So we looked at scenarios, for example, when external contacts were reduced still by 80% or 90%. In a lot of cases, this is the time when you sort of started the social distancing overall, and this is the time where you decided to allow these household bubbles. And in most cases, you see that that can cause disease rebound, or at least stop of disease decline. And that is more optimistic prediction if at the same time emerging households, you cause further reductions in external contacts. Like, for example, maybe now if you've merged households, you don't need to seek outside assistance with childcare or something because now you have someone else to help with that, for example. But these type of strategies are complicated, and understanding, again, the parameters of disease transmission in households is really necessary to understand whether such measures would be reasonable. So this work eventually led us to consider actually another policy that was really being hotly debated a few months into COVID, and really related again very closely to this idea of household size. And this has to do with policies related to controlling evictions during COVID. So what do I mean by that? So, obviously we all know one of the big downstream consequences of COVID and the policies to it was really like an economic crisis and huge increases in unemployment. This is a graph of the US from 1950 to 2020, showing unemployment levels fluctuating over time, and really this like massive and unprecedented spike that happened in the spring of 2020. And so one of the predictions of this from kind of housing policy advocates was that we are going to have tons of people who can't pay their rent anymore. I think roughly in the US, it's around 35–40% of people, I think, who are renters overall. It's probably not so different here, and that this would lead to a lot of people being evicted. Evicted means when your landlord can tell the city or wherever that you haven't paid your rent, and then a law enforcement officer can forcibly remove you from your home for non-payment. So really early on in the pandemic, a lot of jurisdictions made some very emergency temporary bans on people becoming evicted, just as a way to sort of save people from this predicted like massive crisis in housing. There were different sort of economic and policy analysts who really tried to estimate based on careful survey and economic data how many people were at risk of eviction, and the numbers were like quite terrifying. In general, in the US, and again, probably similar here, many people are really paying rent at like the absolute limit of what they can afford, and that's like with their regular paycheck. So, inspired really sort of by this social reasons more so, some places put these temporary bans on evictions and saying people could stay in their apartments even if they couldn't pay. But pretty early on, this obviously became very contentious. There are many people who didn't like these policies and started advocating very strongly against them, and many of these were set to expire, and there was a debate going on, should they be kept, and should the national government step in and make some type of policy that applies to everyone related to evictions. And originally this discussion was, again, more about like the social aspect here, but some people realized pretty quickly that actually this was also an epidemiological concern. And why is that? So the idea is that what actually happens when people get evicted from apartments, and the most common thing actually is that they move in with another household. So this is called doubling up. So most people basically get like a merging of households when evictions happen. And based on what we've been talking about, you can see why that would be an epidemiological concern. Now you have these very crowded, very large households that are at high contact and risk of transmission. Of course, we also have an even worse situation where some people will become displaced and go to shelters or other like communal living situations, which are obviously even more at risk for transmission. And we can like roughly quantify from previous studies kind of what % of people these things happen to. There is some uncertainty here, but the predominant thing that actually happens is this doubling up. So we used our model to really study kind of this time course where you have some social distancing measures happening, and then kind of at the time where these measures are starting to relax, you have many people who are going to be evicted and lead to this kind of change in the household structure where you get these formation of larger, higher risk households. So we built this into some larger models to try to make some more quantitative predictions about how this might impact disease spread at a population level. And so we kind of took two different approaches. we are interested in this phenomenon primarily in cities where renter populations are higher and transmission risks are higher. And so in one approach, we actually looked at all like 100 major metropolitan areas of the US, looked at the epidemic trajectories up to and during the time period where this was being considered. We clustered those and found that pretty much all of those trajectories could be described by 4 basic patterns, and then we use models to like recreate something like those average patterns. And we wanted to do that so by realistically simulating the epidemic state at the time these policies could or could not be enacted, to make sure that we had reasonable estimates for how many people had already been infected, how many people were infected, how many households might have someone with infection, because that impacts all of these predictions. And then we sort of use these like imaginary representative cities to look at these policies across a range of scenarios. And then we did one very city-specific data-driven approach too. We had very early on been interested in the case of the city of Philadelphia. It was one of the earliest places to enact these policies, and one of our close collaborators lived in Philadelphia and was involved in those debates, and it sort of became like a model city for this at a national level. And so we built a really data-driven model of Philadelphia in particular, where we actually looked at the zip code level, found that basically across the city, zip codes could be clustered based on relevant demographic factors into like 3 main categories, and that those zip codes, they were kind of based on like income and demographic levels, and they had different rates of eviction kind of at baseline, different levels of individuals maintaining essential worker positions, and different amounts by which outside contacts were reduced during the epidemic or not, and yeah, different incomes that made them more at risk of sort of COVID-related housing insecurity. And so we use these clusters to recreate a contact network that really sort of had contact structures that made sense for each of these different sorts of zip codes across the city. And we used really high resolution mobility data to construct like a time varying contact matrix for how individuals contacted individuals outside their houses in different sorts of demographic groups, and also based on where individuals were likely to move if they got evicted. So we'll just show you the results for the city of Philadelphia. I think it's qualitatively very similar across different cities. So what we were able to look at is this prediction for levels of COVID infections as a function of time, based on whether or not evictions were allowed to occur if these eviction bans have expired versus if something more permanent was enacted. So basically, there's a time here. This is September 2020, which was like the time at which existing policies would expire. Basically, the main result is that even though it's not like a massive percent of the population that's at risk of evictions, based on data, we considered values that work out to like around order of a few percent of the population of renters experiencing eviction every month. We're kind of parameterizing this by the fold by which eviction rate increases during COVID compared to before COVID. But this still has a very measurable impact at a population scale. So here, this is our prediction for the increase in the percent of the population infected over this year period with and without the eviction bans, and just in terms of like absolute number of excess infections. And in a population, Philadelphia is around 1.5 million people. These are tens of thousands or more infections that are predicted to be able to be prevented by having a ban on evictions and household crowding during this time. And so we can also look a little more carefully on how this risk was distributed across these different demographic groups that are sort of ranging from less to more affluent. And one thing these sort of models can help us do is we don't actually know like COVID burdens by these different groups. The level at which COVID is reported is really at like a county or city level, not like every zip code. So we could really only calibrate the model to like overall seroprevalence of infection, but then based on the parameters we put into the model, it has a prediction for how that's distributed across these different demographic groups. And based on the values that we have, it really predicts that there's a much higher burden in certain demographic groups. This is like one of the zip code clusters versus in others that are more affluent and could reduce contacts more. And then we can make predictions for, in the presence of evictions, how much does the risk increase for different groups? And interestingly, for the individuals who do experience eviction or who sort of receive evicted households versus those who don't, across all of these different clusters, you see an increase in projected infection risk, even though some of those clusters, there's not very many evictions happening in them. For example, in the more affluent cluster, which is C1, the pink one. So the important kind of takeaway here is that when you have policies like this that are meant to prevent infection risk from increasing in most vulnerable parts of the population, in this case, individuals experience eviction, decreasing that risk actually has spillover effects like for the whole population, even though it might seem like a small portion that's being targeted, and that's true, even in very segregated cities like Philadelphia. So this ended up making it to the eyes of the CDC, which we were very excited about, and was actually sort of cited as some of their motivation for eventually enacting this national eviction ban, and then for keeping that ban in effect after a few months when it was set to expire. So overall, this ban was in place for around a year and really prevented most evictions at a national level during that time. And in order for the CDC to enact something like this, it really had to have some proof that this was relevant to disease spread. I mean, that's the only jurisdiction the CDC has to make rules. So having both empirical evidence of the role of households in COVID spread that came from epidemiological studies and a model that showed how that could kind of spill over to population level risk and how it was related to evictions helped them make this case. And it also helped many court cases where individuals sort of with landlord interest groups tried to oppose this legislation. But eventually, after a year, those guys won out and these bans were removed. And now, since then, various economists and other statisticians have tried to do retrospective analysis to understand like how many cases were actually prevented by these bans, not using any type of disease model, but really like observational data. And they also come to the conclusion that these had an important effect. So yeah, maybe just onto the last topic here. So talked a lot about the role of understanding the transmission dynamics in households to making all these predictions. Many of these predictions were made under quite a lot of uncertainty about that. So I'm going to tell you a bit about how we can actually estimate these parameters in households, and not only disease parameters that we think of as being important for a household, like how likely are you to infect your household member, but other disease parameters that are just overall interesting, and then households provide a cool setting to estimate. So in particular, one of the things we were really interested in is variation in infectiousness, something that's also commonly called super spreading. So the idea here is that we think for many infections, individuals kind of have different, on average, number of secondary infections that they will cause, even if they have the same number of potential contacts they're exposed to. And variation beyond what would just be expected sort of by random, like binomial chance. There are many factors that we think determine this in terms of like host behavior and host physiology, in terms of the pathogen itself, and in terms of environmental conditions. But we think it's important, and we would like to be able to measure it. Why do we want to measure this? A lot of cool theoretical work has shown that this degree of variation impacts a lot of predictions you make about disease dynamics, anywhere from predicting like the final epidemic size. It doesn't just depend on like average R naught, but also on this degree of variability across individuals. And in particular, in sort of targeting interventions, if we can identify things associated with transmitting more and target such individuals that can help reduce disease burden with lower resource usage. And this is the logic behind certain vaccination campaigns. For example, how do we measure this? A lot of times people try to measure this variability from contact tracing studies. So these are two examples for original SARS in 2003 and for COVID of situations where we really mapped out one individual and who they transmitted to in some outbreak that was carefully observed. You can clearly see here huge variation between individuals in sort of onward transmission. But the problem is this data is really biased in that you are much more likely to find a cluster if someone infected 100 people than if they just infected one, because if you see at least one of those people, then you're going to go back and try to find the other people. So this is not always an unbiased way of estimating this degree of super spreading. And these type of studies are very hard to do. Similarly, you can have variation between individuals in susceptibility to disease just naturally, also due to a variety of factors from host genetics to host health state, host meaning the person here, to behavior. This also influences some aspects of disease dynamics in terms of how many people you expect to be infected for a given R naught, what is like a herd immunity threshold or a critical vaccination threshold, and also opportunities for targeted control. And it's also extremely difficult to measure, even harder, because you would have to actually know how many exposures people have and see repeat exposures to estimate their individual level susceptibility. So we were curious of whether we could actually estimate these parameters from household data. And so the way that we're thinking about here, and what I mean by household data in the simplest sense, is imagine like sort of before and after, some wave of an epidemic. You can count, go through households and count how many people were infected. And in many cases, you can make assumptions that for diseases in which households are a relatively important cause of infections. So for most infections, if there's multiple individuals infected in a household, it's most likely they were infected by other household members, though we don't sort of always need to make that assumption. But so if we kind of go through and either by following people over time and doing PCR testing or just doing antibody testing kind of at the end of a stage of an outbreak, get this whole distribution of households and the number of individuals infected or not infected in them. And it's been known for quite a while now, almost a century when someone sort of tried to work this out originally, that you can use this sort of data to estimate this first parameter I was talking about, the household secondary attack risk. That's just the probability that if someone in the household is infected, that they will infect, any other given individual before they recover. And so in order to do that, every time you see a piece of data like this, for example, 3 to 5 people infected, you have to think about all the possible ways that could have occurred. This person got infected and they infected these 2 people, or this person infected, they infected this person, they infected this person, or all those possible paths. But if you kind of integrate or add up all of those paths, and you can even write down, if you make a lot of assumptions, you can write down even a probability equation for this. You can go from all of this data to a best estimate, like a maximum likelihood type estimate for this one-to-one transmission probability in the household. And so that is very useful, but there's a few limitations in terms here that this assumes that everyone has the same probability of transmitting to everyone else. And the models that are used for this already do make a lot of approximations even about the disease dynamics. So we took this idea and then extended it to be more general and flexible. And so what we did is not try to calculate anything analytically. We have enough computational power nowadays. We can actually simulate all of this to calculate likelihoods. but then relax this assumption that everyone had the same transmission rate and basically expand this to include these two types of heterogeneity. So basically we have an infection model, similar type of model I showed before, like SEIR infection, but where that sort of beta parameter, like the transmission rate, has some distribution across individuals. And also the susceptibility is distributed across individuals. So we're kind of adding two extra distributions here. And we parameterize these in a way that might seem a little weird, but is meant to be intuitive based on the way people have been trying to describe this sort of heterogeneity in infection dynamics for a long time. So this is actually from a meta-analysis of a lot of different disease studies from over the years where people try to make a summary statistic about heterogeneity just using that type of contact tracing data. And what they try to calculate is what percent of secondary infections come from what percent of primary infected people. And so what they do is basically say, if you look at the most infectious 20% of individuals, how many secondary infections do they cause? Like what percent of secondary infections? So if everyone was equally infectious, then top 20% infectious people would infect 20% of people in the next generation. But actually what you see a lot, and why someone came up with this thing called the 80-20 rule, is that the most infectious 20% of people are responsible for 80% of the infections in the next generation. And all the other people in the first generation like barely infect anyone. That's a measure of heterogeneity. And so we're not going to measure heterogeneity that way with contact tracing studies, but we'll use this number as a way of saying how extreme our distribution is, this P80. So this is like what percent of the population do you need to explain 80% of infections? If it's 80, no heterogeneity. If it's very small, that's a lot of heterogeneity. And we can do the same idea for susceptibility. So what percent of population susceptibility is carried in the most susceptible individuals? So yeah, the interesting thing here is actually just with forward simulations, you can see there's really clear expected signs of this heterogeneity in households. So here I'm showing the distribution of the epidemic size in a household. The household has 5 individuals in this toy example as a function of these different disease parameters. So this one's very simple. This is just the secondary attack risk. So your chance of infecting any contact. The higher that is, the more likely that a lot of individuals in the household are infected, after one introduction happens. So, okay, that's, usually just what we try to estimate from household studies. Then these other parameters, though, they also leave a signature. So as you get more and more heterogeneity, so as you move up to this purple level where the P80 is 20, so 20% of individuals cause 80% of secondary infections, you see a change in this distribution also, where you see more extremes sometimes in households in terms of many times the infection goes extinct. But if it doesn't, you can have larger outbreaks. And sort of in the opposite direction, when you have more variation in susceptibility, you can see like a spreading out of these values across households, where yeah, here you're actually getting a spread backwards towards less infection. But depending on the household size, you see different effects. But importantly, because there are these signatures, you can actually just do this backwards. This is on some simulated data, but basically saying if I observe a bunch of households and then I try to pull out these parameters, what's the average amount of infection and how much variability is there? You can do that, particularly if you have large study sizes. So just what I'm showing here is for a few different study sizes, these are like posterior distributions on their side. What is your estimate for both this secondary attack rate and this degree of variability in transmissivity and susceptibility? And these lines are the true values. And when the distributions are centered on that means you are kind of on average estimating this right, but there's a lot of uncertainty. So you can get kind of the posterior moves towards these values, and these can kind of be unbiased estimates of these quantities, though there is uncertainty. And importantly, if you actually use a model that doesn't include heterogeneity, when there is, you will then get biased estimates sometimes of these values. So we just put this together in a few different real world studies of COVID transmission in households, super different settings. The best study is actually, largest study is actually this one from Public Health Ontario, where they kind of just through their regular surveillance released a massive data set on every household that they had any reports on how many individuals in that household had at some point during the first wave of COVID tested positive in a way that was recorded. I mean, at that time, all tests were recorded because there was no home tests. And then two separate studies, which were actually done sort of specifically for this purpose. One in Geneva, where they really went to households and tested everyone's blood to see any evidence of COVID, so they wouldn't like miss infections that weren't tested. And another one in a community in Israel that had really high household sizes, where they also went in repeatedly and gave PCR tests even to individuals who might not have sought them themselves. From this data, we can make estimates of these quantities. In general, the study that has the most data, the Ontario study, we find that there's really strong evidence for heterogeneity. So estimates like 16% of the population responsible for 80% of spread, and also very strong evidence for variation in susceptibility. We also estimate in all cases this secondary attack rate is somewhere between 25–35%. In some cases, there's a lot more variability in these parameters for small data sets, and it varies a lot between settings, suggesting that this degree of variation might not actually be like an intrinsic property of disease, but depends on a lot of population parameters. So overall, if we compare the model fit to data, we see good agreement in some cases, particularly the Ontario setting. For other settings, there are some times when we see disagreement, particularly in large household sizes. The model, which is the blue compared to the data, which is orange, overestimates how many infections you expect to see in larger households. And we think that's actually because generally infection doesn't scale with larger households the way we would think it is. There's probably less contacts with everyone in some of these larger households. So yeah, just to summarize all of this, overall, we find that the outcome of social distancing measures is really sensitive to the role of household transmission for disease, even if that intervention is not targeting household transmission. Interventions that do target household transmission, such as eviction bans, can have really spillover effects for a population in terms of reducing transmission. And there's this critical link between like housing security and disease transmission. And household settings can be really useful for estimating disease parameters, not just for average transmission rates, but these degree of variability between individuals. But it is hard to get large enough data sets on infection in households to really study this carefully. So, thanks to many, many people who worked on this, experts across a lot of different fields in my group and other schools. We worked with some housing policy people on a lot of this, which was really fun. And yeah, we're just happy to take any questions. And thank you again to funders who supported all of this work in this crazy COVID times when they were supposed to be funding other research.
Thank you so much. Question? Duncan?
Yeah, I'm not sure if I might have missed it, but did you include seasonality in looking at the difference between community rates and household?
Yeah, no, I mean, again, so this was really done like early stage COVID. We still don't have a great idea about the actual intrinsic seasonality of COVID. people have tried to estimate this for other coronaviruses, other respiratory viruses, like huge amounts of uncertainty at that time was not something that was estimatable. In terms of seasonality and contact patterns, I also don't think at that time there's really any data to suggest that. Most of these surveys were sort of one-time things that were done. And even at that time, this like real-time cell phone-based mobility data that was sort of tracking contacts, whether or not they actually have that data from long before COVID, it's like a bit unclear, but never really shared. It sort of only started being shared in the COVID period. So we didn't have like a year's worth of values to look at that. But I think now we do, but other residual effects from COVID are still affecting that data. But I think there is definitely seasonality in that. This is actually something that I don't think has been adequately taken into account in most models, even of more just like endemic respiratory infections, like RSV, flu, for example, what role the like human and indoor environment has. People try to relate seasonality to like the temperature and the humidity and those type of things, but probably a larger driver of this in many settings is like how much time people are spending inside versus outside, you know, whether it's school year or not. So it's certainly something, I mean, people have looked at it, but it could use more attention to like understand those mechanisms, but we just didn't have a lot of data on these human behavioral patterns to do that.
I have two questions,
Mhm.
actually. So one is, you get results for like infection dynamics within, or like the infection burden within households.
Mhm.
But then can we use that in kind of a direct way? Like, do we get for free who to vaccinate? Or do you think?
Yeah, like explain what you mean.
So like so when you look at the clusters of
Yeah.
who then is causing the most infections,
Uh-huh.
it's like immediately for free.
Oh, I see. Yeah. So one thing is that we don't really get from this who. So we can back out whether like this data is best supported by a model in which everyone has the same propensity to infect, or whether there's a huge spread out distribution, which is more what most of the data is suggesting. So then we'll say, okay, we know there's a distribution, but we can't actually say like who falls where on that distribution and why do they fall there, right? Because for any individual, like the outcome was a combination of stochastics and propensity. We can't separate those well. And even if we could, we would only know that like after the fact. So what we eventually would like to do here is, and it's something people have done for sort of simpler models of household transmission, is look for kind of build in models that have covariates that influence these transmission factors. So, you know, whatever properties of an individual you might be able to measure or be interested in, how do they affect like the degree of variability. So people have certainly estimated for households models where like there's one transmission rate at baseline, like an average one, and then another one for like this age group versus that age group, for example, and like estimated both of those things from data. So combining that type of approach with this approach that, you know, we don't need to make any approximations in our model because we have like a simulation-based likelihood, and where we can include this variability that's sort of unattached to traits. Also, that would be best if we can do that. Then we would at least have like some properties related to.
And within the clusters, the other question I had is about evolution.
Mhm.
So viral evolution within the
Yeah.
period. And I mean, even just related to what you were talking about yesterday within a host, but like
Yeah.
between hosts, the more
Mhm.
infection contact or the more transmission there is in the chain, the more likely or
Mhm.
potential you would have for evolution. So have you thought about integrating that, or is that important?
Yeah, no, I think it's important. Yeah, I haven't gotten into that at all, but it's something we have looked at in some cases. Basically, like overall, when you have like really clustered transmission, and so then at any time you have like clusters of the population where there's more immune people and clusters where there's less immune people, due to the natural like spread of the disease. So like before anything to do with vaccination, then that actually makes it easier for new variants to appear that are immune evasive. And that happens at all scales, I think, whether it's like within a community or like around the world. And the reason is actually kind of similar to things I was talking about yesterday. So when you have like sort of clusters of naive population, meaning people that are fully susceptible, then the wild type virus can easily spread there. And the more spread there is, the more opportunity for generation of variants, like just production of mutants that have different properties. So that's one step of evolution, the mutation step. Then the second step of evolution is selection. And so when you have other clusters of the population where once a potential immune escape strain gets in there, it can spread very well because everyone that it's spreading to is all immune and it has a benefit in all of those people, then that will provide the strong selection for an immune escape variant. So those clusters, combination of having those two clusters makes evolution proceed fastest, which as the alternative being when you have just like totally well-mixed population where susceptible naive and like previously infected and partially or fully immune individuals are all like totally mixed. That is actually like harder for evolution most of the time, if that makes sense. That's a very qualitative argument, but like you can show these things mathematically too.
Right, well.
Thanks,
you so much,
everyone.
Alison, and